I'm Antonio Sala, and in this video we are going to discuss further insights on the relationship between the singular value decomposition, principal maneuvers, and the intuition, let's say common sense, on how to choose a subset of sensors or actuators, a subset of controlled or manipulated variables respectively, or how to fuse some of them, by common sense. But okay, if we know the technology, of course we can apply common sense. The goal of this series of videos is understanding that SVD replicates common sense, so we can use it if we don't fully understand the technology to get that fusion or subset suggestions, or conversely, by looking at the agreement between common sense solutions and singular value decomposition output, we can better understand SVD. Let us briefly review previous videos and motivate what we are going to do now. In previous videos, we discussed some imaginary temperature control processes, and for instance, in here we had one manipulated variable, resistor, and 3 sensors. And of course, even if we could do singular value decoupling, and it would propose a sensor fusion contouring a weighted average in which the center sensor is doubly weighted, well, we could just decide that a much simpler alternative with maybe similar practical results would be just controlling the center sensor, thus placing a single PID in the most important sensor. And well, basically for reference tracking, it would possibly work just quite similar to the full weighted average stuff. But there may be difference in disturbance rejection. If somehow disturbances do not have the symmetry, the gain matrix, in the same direction as the resistor. But okay, this is one motivation for just choosing a subset of a sensor. Regarding the actuator side, we have other examples, such as this resistor plus blower setup, in which, well, the principal maneuvers suggested a fusion in which control authority from the PID controller was split proportional to the gain, but if the blower had twice the effect of the resistor and temperature control corrections are also apportioned double to that blower actuator, then we may be just happy with a much simpler control in which we can just get a subset and use the blower only, leaving the resistor in a constant operating point. That would be simple to explain and maybe simple to maintain, and we would lose, let's say, only 20% of control authority, at least in this scheme, because in this one, double the size, double the coefficient here. The overall control authority splitting would be 4-1 to the blower. Well, these are the ideas on subset of actuators or subset of sensors inspired in SVD results, or well, in just common sense. Choose the manipulated variable with higher scaled gain, or choose the sensor with higher scaled gain, and stop doing multivariable things if a simple solution may work in your practical simple application. Now let us consider the example we are continuing in this video, which was this one, in which I had 2 resistors, 2 blowers, and 3 thermocouples. I had a 3x4 transfer function matrix whose gain was this thing, scaled this one, and the singular value decomposition was like this. So as this gain was very low, I decided not to control it and incorporate it to the practical null space, apart from the theoretical null space like here. So I will control these 2 things, these 2 principal maneuvers. Now I can do it in 2 different ways. One, carry out the full SVD decoupling and propose this controller structure, in which I have one controller for the green principal maneuver 1, in which these things are the columns of U. And this thing is the column of V. And similarly for the principal maneuver 2, the first one was the overall heating everything up, down. And the second one was the temperature difference between left and right sides. That would be the mathematically recommended way of using all sensors and all actuators aligned with the principal maneuvers. But, okay, now let's go with common sense and say, look, if we wish to understand the principal maneuvers, controlling all temperatures and left-right difference would be intuitively somehow similar to just controlling left-right temperatures, in the sense that the center temperature is not too important in the second maneuver, and in the first maneuver the center temperature has exactly the same weight, let's say, to the right sensor and to the left sensor, so it's the center temperature would do exactly the same as both sensors 1 and 3, and in the second maneuver center temperature will do nothing. So we may wish to recommend a simpler structure in which we just disregard the center sensor and just forget about that one as a control variable and use only 2 control variables. Okay, that's of course a very intuitive option. If we analyze the singular value decomposition of the resulting matrix, let us compare with 2 maneuvers with which to control. This is the selections of just outputs 1 and 3 as controlled variables, and the singular value decomposition is this thing, so the interpretation is more or less the same as before. I can control principal maneuver 1, temperatures 1 and 3, common way, the average of them, and in here, second principal maneuver is controlling the difference between right and left temperatures. So the resulting SVD has the same interpretation as the full SVD with the central sensor, so we are basically doing the same. And my input-output controllability measure, the minimum gain, and maximum, 1.13, 2.45. Well, these ones are slightly less than the one with 3 sensors. Of course, the norm of the output, the more sensors I put, the more variation I observe. But okay, the minimum gain is basically the same. And of course, if I use the different sensor combination, let's say 1, 2, then minimum gain will be 0.5, or the other 1, 2, 3. Minimum gain will also be 0.52. But with sensors 1 and 3, I get almost the minimum gain as I had with 3 sensors. So the more difficult maneuver in my original 3 sensor setup is sort of well captured by this sensor subset. So this seems the best choice. And of course, that was also the intuition behind this SVD with 3 outputs in which, all temperatures coordinated up and down, or left minus right temperature difference, hinted me that using just sensors 1 and 3 would be very close to this principal maneuver control. So I use this thing. Further mathematical justification would be, let's say, computing the angle between the 2 principal maneuvers, these 2 columns of view. So these 2 vectors span a plane, a 2D subspace in 3D, then the projection of that with respect to the first 2 coordinate axes, this one, they are separated 65 degrees, but the angle between that principal maneuver plane and the one with the first and third axis is only 33 degrees, and the other one, sensors 2 and 3, is 68 degrees. So again, the angle spanned by the principal maneuvers and this coordinate plane is the lowest of all combinations 1, 3, 1, 2, 2, 3. So this is the justification for the common sense interpretation of these two columns of view, which is, okay, just forget about the center sensor. As you see, we complicate things because we want to understand the relationship with SVD, but of course you would not explain that to a plant technician, and you would just tell him that, okay, you know, it's common sense to control just left and right temperatures separately. So we would propose something like this, in which, okay, forget for the moment being about the actuator stuff. We control temperature 1 and 3 with a PID for the left and right hand side thermocouples, and then we need to discuss the manual fusion or whatever of subset of actuators, of manipulated variables, and we will apply similar common sense ideas plus a justification with singular value decomposition. So now we decided to control only this G2 matrix, so we will concentrate on the input directions of this reduced output matrix G2 in order to check whether we can fuse or subset actuators or whatever. Then, of course, the full SVD decoupling would indicate that these two columns of V2 should be arranged with something similar to this, which was with 3 sensors, but as you can see, the numbers are very similar because we lost almost nothing by neglecting the central sensor. So the actuator side would be very similar to this, and of course the sensor side indeed changes these coefficients because we have eliminated the central sensor. But okay, the thing is that that would be the SVD stuff, but now our intuition tells us that if we are controlling left, right independently, then we should be able to either select a subset of actuators. If we are controlling 2 things, maybe we can live with 2 actuators instead of 4, or we can coordinate the motion, coordinate the control authorities of the ones at the left and the ones at the left and the right like this, somehow manually without thinking on SVD. And indeed, you know, basically the coordination would end up being that if the PID left, let's say, says heating, then I should increase the resistor and decrease the blower. The only remaining question is by how much? Why these numbers of 1, 1.5, you know, because okay, the blowers have a little more gain in scaled units. If we see here, columns 1 and 3 refer to resistors, columns 2 and 4 refer to blowers, and yes, you know, from 1 to 1.6, it's kind of the increment of gain, or in here, 0.9 to 1.4, you know, it's kind of, yeah, 1.5, 1.6 gain increase. So with this kind of weighting, we can just fuse the actuators, and it should be somehow similar to the ones given by the principal maneuvers. Let us check that. But first, let us just imagine that we don't want to get this complication, and if the blowers are more powerful, we may just think in setting the resistors to a constant set point and using only the blowers to blow cold air. So if we want to cool, then we increase the blowing power. If we want to heat, we decrease the blowing power. Would that work? Let's see. If I only consider using to control these 2 temperatures the manipulated variables 1 and 2 at the right hand side, then there is one thing we cannot control. Of course, that would be the left temperature. If I choose the 2 resistors, actuators 1 and 3, I have somehow some control authority, 0.63, but not 1.1, which was the full control authority. So I lose a lot of capability to control these temperatures. If I get 1 and 4, again I get this, 2 and 3, this, I mean, if the blowers are the most powerful, of course, we know from common sense that the choice of actuators 2 and 4 should be the one that, if I am restricting to a subset, I should choose. The other one is rubbish. So I have 0.94 minimum gain compared to this 1.14. So sort of I just lost 20% of control authority by using the blowers. So depending on my ranges, it might be a good enough solution. Just use my PADs to control these blowers and forget about actuator fusion. But okay, in this case, if in my scaled units I wished to have a control authority minimum gain above 1, then this subset of actuators, blower only, is almost there, but not quite. I need a little more, so I will go for the full fusion we see here. Why? Well, because if I now divide this by this and this by this, 0.56 divided by 0.34 and 0.62 divided by 0.41, then we see that in the principal maneuver 1, the proportionality between the right hand side fan versus resistor is the first maneuver 1.66, in the other 1.51. So I choose something in the middle, 1.58. Well, negative, because in order to hit, we must increase resistor or decrease blower. And if I now divide 0.64 divided by minus 0.39 and 0.54 divided by minus 0.37, then I get these ratings for each of the principal maneuvers. And well, somehow, the mean of this is 1.56, something like that. I just invented a little bit. So with this kind of weightings, that would be the optimal fusing of these manipulated variables to approximately interpret what the singular value decomposition tells me. But okay, the important thing is that I would explain to a technician by common sense, saying that, okay, if the blower has a little more gain, then I will give him a little more control authority proportional to its gain in this kind of fusion, 1.5 or something like that, extra weight regarding the resistor. So this would work. And the only thing is that in order to simulate things in MATLAB, as this column vector and this one do not have norm 1, then they alter the gains. So the new SVD, the new scaling somehow is altered. So this matrix is the change of variable we are seeing here, but in the final solution, I would divide these two numbers by the norm of the vector 1, 1.58, and these two numbers by the norm of this vector. So my matrix F will have columns of norm 1, just as the principal directions we saw, and then the interpretations of the scaling and the SVD singular value gains will keep unchanged. Then with this change of variable, I have this 2 by 2 matrix with this new scaling, and then the PIDs would see this 2 by 2 G3 matrix as apparent transfer function gain. And if I compute the SVD 2.45, 1.13, it's basically the same gains as the ones with two sensors and full SVD decoupling of the 4 actuators, so I am losing nothing by this handmade fusion of left and right actuators. So in this way, I get a left loop, right loop for temperature control that would be much easier to explain to a non-expert than this full SVD decoupling stuff. This seems so much simpler. Furthermore, if I just put here 1 and 1.5, just forget about the third significant figure stuff. And indeed, the G3 I obtain that would be seen by these PIDs is this thing. And if I compute the relative gain error, for instance, to check that the pairing is correct, which of course it is by just common sense, I would not use the left temperature sensor to control the right hand side actuators. I would be crazy. Then indeed, this G3 provides almost the same SVD, and the relative gain array is a good one, close to unity in here, 1.15. So my problem is well conditioned, and PIDs for slow tunings, we are just using the DC gain, would work reasonably well with this pairing, which at the end, as fused actuator 1, 2, this new actuator 1 controls the right temperature, then okay, actuator 1 controls the right temperature, actuator 2 fused controls the left temperature, everything is perfectly okay, coincident with common sense. And so this would be the simplest structure I could explain that doesn't lose control authority, because I use the 4 actuators and we don't lose too much by just forgetting about the center thermocouple. So this subset fusion can be done by either just common sense manual thinking on my actual technology in my plant, or well, it may be suggested by the output of the singular value decomposition of the gain matrix, and you can explain in whatever way you wish to your customer. And if you decide for a simpler setup, you can propose this control structure instead of the whole SVD decoupling, which will be more difficult to understand for the non-expert audience. And if things are more complex and difficult to understand, they are more difficult to maintain maybe. So apart from a different disturbances section behavior, if I expect strong disturbances in the center sensor, if I do not expect that, then maybe my final recommendation would be this simplified 2x2 left-right temperature control. But of course that depends on the application. But the goal of this video is just understanding the relationship between common sense and SVD. So we end here the case study, hoping you have understood these common sense interpretations. Thanks for watching.